Hello, everyone. Welcome to the next guest lecture. So today we have Jenny Wilson here, who will tell us about configuration spaces. And you can see her links to the Jamboard in the chat. So please click on that if you'd like to follow along. Oh, and how would you like people to ask questions if they have any?
Oh, please, I don't know, any method you're comfortable with, please feel welcome to pipe up. That's probably the easiest way to get my attention, is to yell at me, since I have like 4 windows open that I'm juggling between to give the talk. I might not see the chat right away, or maybe I can nominate Simon. If somebody has a question in the chat, maybe you can yell at me, and then I will see that it's there. Otherwise, please just pipe up, and if you're comfortable, unmute yourself and yell at me. I'm happy to field questions, very happy. Great. So, right, thank you very much for the invitation to speak today. It's awesome to be here. This is a talk, at least at the end of the talk, I'll say something about configurations. More generally, this is intended to be an introduction to the sort of research that I do. I'm a mathematician at the University of Michigan right now. And I do work, broadly speaking, in an area of mathematics called topology. So I thought I would start the talk with a bit of an overview on, at least informally, what I mean when I say topology. So great, hopefully I'm sharing my screen and you can see the Jamboard. There's also a link to the Jamboard, which you can click on optionally, and it means that you'll have the option of referring back to previous slides if you wish. Okay, so opening question, what is topology? And very broadly speaking, topology is the mathematical field that studies shapes. So I'll hopefully narrow in a little bit more on what I mean by the word shapes, but let's start by looking at a few examples. So some examples of topological spaces. The first I've drawn here are just 3 isolated points. That's an example of a topological space, as would any number of isolated points be, including infinitely many. Another example that you've probably encountered before is the plane, sometimes called Euclidean 2 space. Another example you may know is the circle. That's a topological space. A line segment is a topological space. The torus is a topological space. So that by the torus, I mean the surface of a donut. And similarly, we could take donuts with more holes in them, or I guess handles is the mathematical term. I could take a donut with, here's one with 2 handles. I could take one with 100 handles, and then its surface, the surface of that donut is called a genus G surface. If it has G handles, here's a picture of a genus 2 surface. Okay. And right, a topological space, whatever that means, whatever that structure is, if we have a collection of topological spaces, then we can use that to build new spaces using a variety of operations. For example, any subset of a topological space inherits a topological space structure. Unions of topological spaces are topological spaces. Cartesian products are topological spaces. And some of these operations will feature later in the talk. Okay, so to narrow in a little bit more on what I mean by topological space, being very informal, a topological space is a set with some extra structure on it. And roughly speaking, that extra structure is a notion of what it means for 2 points to be close together, very broadly speaking. And in general, it turns out that the structure, the definition of a topological space, is exactly the structure that we need to make sense of the idea of continuous maps between topological spaces. So let me say, for the purposes of this talk, I will try to stay concrete. I will try throughout the talk to work mostly in terms of examples like these ones, which I'll say more about in a moment. Secretly, this list of examples that I just gave you are all drawn as though they are subsets of Euclidean 3 space. So everything I've drawn here sort of embeds in our 3-dimensional world. And for that reason, I think everybody here has a very good idea, has good intuition for what we mean by the topology on this space, even if you've never heard the word topology before, because you have so much experience living in the 3-dimensional world. You have good instincts for what the topology on Euclidean 3 space is.
There's a question in the chat. What do you mean by a notion of what it means for points to be?
Great. So I am going to I'm not sure I'll ever answer that question to total rigorous satisfaction. Let me say something about what I mean for points to be close. And if you want me to get into gory details afterwards, then at the end of the talk, we can try to pin down something actually rigorous about what it means for points to be close. Let me start with something informal. So here's a technical digression. This technical digression is something you're welcome to ignore for the rest of the talk if it doesn't speak to you. But this is a hint at what it would take to make this idea of a topological space precise. And the key is, we'll start with understanding the topology on the real number line. So on the real number line, a subset of real numbers is called open if it, first of all, if it's empty, the empty set is open. Or more generally, if it is possible to write it as a union of open intervals. Okay, that is the definition of an open set on the real number line with its standard topological structure. And here's an exercise. This is a challenging exercise, I think, if you haven't done it before. But if you have seen a rigorous definition of what it means for a function of the real line to be continuous, for example, if you've seen the epsilon delta definition, then you have the tools you need to tackle this challenging problem. I claim that a function from the real line to the real line is continuous if and only if the pre-image of every set U, so the pre-image is defined here, the pre-image of the set U is defined to be all points that are mapped by F into U. So it's continuous if and only if, whenever U is open, the pre-image is also open. That is equivalent to the definition of continuity. And so it turns out that this concept of what it means for a function to be continuous is completely characterized by the function's behavior with respect to open subsets. And so in order to generalize the idea of continuity to an arbitrary set, what we need, it turns out, is a notion of open subsets. And then this condition will become the definition of continuity. A function is continuous if and only if the pre-image of every open set is open. Okay, so that statement definitely shouldn't be obvious if you haven't encountered it before. I'm going to move on to the next slide in the talk. And so this is exactly where we get the idea of a topological space. A topological space is a set plus like a formal declaration of which subsets are open in our set. And again, this turns out to be exactly the structure we need to make sense of things like continuous functions, convergence of sequences, and many of these other concepts that you've maybe encountered in your calculus class. So that is topology. And right, this is what's written here. So the concept of an open set is exactly what we need in order to generalize concepts like continuous functions. And so formally, a topological space is a set plus the data of which subsets are open. It's a completely abstract definition. Okay. And so in answer to the question, formally what it means, 2 points are close, is if they are contained in a lot of common open sets. They are subsets of many of the same open sets. They're elements of. Okay. All right. So I wanted to contrast these. This is the definition of a topology on a set. This is what I study, topology. This is distinct from the field of geometry, which I think you could also refer to as the study of shapes. But in geometry, shapes are much more rigid objects. Okay, so as we know in mathematics, we need to be very precise about exactly what structure on our objects we're studying. In topology, we're just studying these kind of squishy shapes. In geometry, shapes are much more rigid objects. And specifically, I mean, there are different geometric structures you can define on a set, but the sort of structures that a geometer might study would mean, for example, their shapes come with things like a notion of distances between points, or a notion of angles between different rays. Or if you're in some sort of differentiable setting, you might have a notion of areas or volumes or hypervolumes of subsets of your space. So these are all concepts that live in the realm of geometry in contrast to topology. Okay. So that is to say, to a geometer, shapes are rigid objects. And to a geometer, here's an illustrative picture. These two triangles may be considered the same triangle because they're similar triangles. But this triangle, it would not be the same as either of these, since metrically they're different. This triangle has a much smaller area. This triangle has different side lengths. So those are not the same triangle from a geometric point of view. Okay, so in general, to a geometer, two geometric shapes would be considered the same if they differ by a rigid motion, like a rotation or a translation. But I wouldn't be allowed to do something like stretch or scale my object. That would give me a new geometric object. Okay. So let me progress to slide number 3 now. Okay, but I'm a topologist. So in my universe, shapes are floppy. Okay, they're just defined in terms of open subsets, whatever that means. But what it does mean is that we can manipulate them continuously. In my world, I view shapes as being made out of something like putty, and I'm allowed to deform them continuously as long as I don't tear them. That would be a discontinuous operation. So in the world of topology, I'd say we can squish, stretch, or continuously deform these shapes as long as there's no tearing. And in my universe, here are all of these shapes that I've drawn here, this triangle, this larger triangle, this circle, and this square. These are all the same topological shape, and they're all an example of the shape I would call the two-disk. Okay. Though in contrast, a two-disk is not the same shape as a circle. Those are topologically different shapes. Okay. And similarly, it makes sense as a topologist to talk about the torus or the donut, because from my point of view, all tori and all donuts, no matter if they're big or small or thin or bulky or anything, those are all the same topological shape. And this is where
There's a question. Why aren't the two disks in the circle the same shape?
Oh yeah, great. So that is a great question, which I guess in general, it's a lot harder to show that two shapes are not the same shape instead of showing that they are the same shape. Somehow to show that these two shapes are the same shape, then I would just need to show you that I can kind of continuously deform one into the other one. Or I guess to be really precise about it, I would want to find a continuous function that takes this circle to the square and that has a continuous inverse that takes the square back to the circle. If I can demonstrate the existence of those functions, then that's what it means in a technical sense to a topologist for these two shapes to be the same. A harder question is to show that two shapes are not the same topological shape. The technical word is homeomorphic. So I would say these two shapes are homeomorphic to each other. These two shapes are not homeomorphic to each other. And it's in general much harder to prove the non-existence of a homeomorphism, to show there's no continuous invertible functions between these two shapes. But topologists have developed a number of tricks, I guess, a number of what are called invariants of topological spaces that you can use to show that they're not equal to each other. And in fact, sit on this question. I will come back. I will, in a couple minutes, I will show you an example of an invariant that we can use to argue that these are not the same topological space. So hold that thought. It's a great question. All right. Oh, yes. And as a final thought on this idea of homeomorphism, this is where we get this joke that a topologist can't distinguish their donut from their coffee mug, which is absolutely true. Those are homeomorphic. Those are the same topological space. So if you ever need assistance with breakfast, you should find a geometer and not a topologist, because they can, in fact, distinguish those spaces. But I cannot. They are the same. Okay. So here's a trick that will be, that's a neat mathematical construction or perspective or something, which will also maybe feature later in our talk. And that is that we can define or represent topological spaces using formally what's called the quotient topology, but what I really mean is kind of a gluing construction. And here are some examples of what I mean by that. So one way that I could represent a circle is by just an interval plus the gluing instructions that say I should glue these 2 points together. So I'm going to impose some relation on the space that says these 2 points are in fact the same point in my topological space. And hopefully that's believable, that if I take an interval and I glue together the endpoints, the result is a circle. All right. Similarly, here's a slightly more advanced version. Here's my picture of a cylinder. And I can represent a cylinder by taking a square, just a square. This is my 2 disk again, a square in the plane, but then gluing together these 2 edges. So this means I'm going to glue this point to this point, and this point to this point, and this point to this point, and so on and so forth. And let me see if I have a piece of paper handy. Hopefully this is believable. If I take a sheet of paper and I glue together 2 of the edges, then the result is in fact a cylinder.
There's another question. To go from a circle to a line segment, don't you need to make a tear?
Yes, absolutely. Yeah, that's a great question. To go from a circle to a line segment, don't you need to tear? Yes, you do. A circle and a line segment are not the same topological space. They are not homeomorphic to each other. And so this is what I've drawn here is not just a line segment, but it's a line segment with this extra data of gluing instructions, where I have formally proclaimed that now these 2 red points are in fact the same point. And so this is not a line segment, but what is technically called a quotient of a line segment. It's a line segment, plus I have glued together some of the points. And right, my claim is that if I take the line segment and then impose this extra relation, that these two red points are now equal to each other, they're now glued together, then that space is no longer a line segment. It's not homeomorphic to a line segment. It is now a circle. And my claim is that, or the takeaway I hope that you get is that this gives us another efficient way to denote a line, to denote a circle. I can write down my circle as this line segment plus some extra gluing instructions. And that's I'm glad you made that point. That's a really important distinction. So a line segment and a circle are not the same topological space. And that's why I need to perform this gluing construction.
All right, that makes sense. Thank you.
Awesome. Awesome. Oh yeah, right. And then this is let's take this cylinder construction a step further. And this is something I encourage you, if you haven't encountered this construction before, you should definitely like get a washcloth or something and play with it until you convince yourself that this works out. But I can write a torus as a quotient space in the following way. So first, I'm gonna start by building my cylinder. I'm going to start by taking a square and gluing together these two edges, and that gives me a cylinder. But then I'm also going to glue together the two top edges, the top and bottom edge. So that means I'm going to glue this point to this point, and this point to this point, and so on and so forth. So that's like taking my cylinder now, and I'm going to glue this circle at the top to the circle at the bottom. And my claim is that when I do that, the space I get is a torus. And great. So I think this is a cute construction, but on top of which there's many practical reasons why you might want to draw your torus as a square with these edge identifications in the plane, instead of as a instead of this picture. There's a lot of like mathematical arguments that are much easier to see with this visualization of the torus instead of this one. Cool. Okay, so right, big question. What features of topological spaces are mathematicians interested in? And there's a ton of answers to this question. I personally frequently study invariants called homology and cohomology of spaces, which unfortunately would take too long to define today. But let's focus on the following two examples. So one example of something that a mathematician might study are paths in a topological space. And you should definitely, for this talk, just think of a path in terms of pictures like this one. I have 2 points in my space, and my path is, here's a little path I've drawn between them. If you want to be technical, then the technical definition of a path is it's the image of a continuous map from an interval into the space. Okay. And one topological invariant of a space is path connectedness. So a space is path connected by definition if a path exists between any 2 points. So fix any 2 points in the space. If it's path connected, then it's possible to draw a path between those 2 points. Okay. And this is called a topological invariant. What I mean when I say topological invariant is I mean if 2 spaces are homeomorphic, if they're the same space, then if one of them is path connected, so is the other one. Which means that this gives us one tool to distinguish a space from a space that isn't homeomorphic, one tool we have is this idea of path connectedness. If one of them is path connected and the other one isn't, you know they're not homeomorphic. And unfortunately, that observation is not enough to distinguish the disk from the circle, because here's an exercise for everybody. Both of those spaces are path connected. If you take any 2 points in the circle, for example, it is possible to draw an arc between them. And so the circle is path connected. Similarly with the disk. All right, and here's an illustration. So if you take a disk is path connected. You give me any 2 points in the disk, I can draw a path between them. However, the union of 2 disks is not path connected. If I choose a point in this disk and a second point in this other disk, there's no way to draw a path from one to the other. So the union of 2 disks is an example of a space that's not path connected. So 2 disks not homeomorphic to 1 disk. Not the same topological space. All right. So let's look at another example of something that topologists study. I'm going to move on to slide number 4 now. Okay, so the next feature of spaces that is commonly studied by topologists are, oh, there's a question I see. Are there any non-trivial examples of not connected spaces? Absolutely, there are tons. Spaces, I mean, one, so I don't know, we could debate what trivial should mean in this sentence, but one, trivial way to make disconnected spaces is to just like take various spaces and sort of plop them next to each other and say, I'm going to like take the union of these spaces. So yeah, exactly. Great. So in fact, what I just described is formally called the disjoint union of spaces. And that's right. That is a cheap way to construct spaces that are disconnected. But there are spaces that are disconnected that still have really rich topologies. One example is the rational numbers. So the rational numbers is a subset of the real line, is a space that's disconnected. In fact, if you take any two rational numbers, there's no path between them. So it's a space that's very, very, very not path connected. And yet its topology is still very rich. And another interesting example, you should Google search the Cantor set. And this is another example of a space that is somehow very, very, very not path connected and still has a very rich topology. So I'll type this in the chat. Two non-trivial examples, rational numbers, and look up the Cantor set if you haven't before. Okay, cool. So let's talk about loops in topological spaces. And I'm on slide number 4. Yes, on slide number 4. Okay, so again, you should think a loop is what you think it is. It's like draw a little circle in the space. The circle should not be torn up in any way. It should be somehow a continuously drawn circle in your space. That's the intuition. If you want to be technical about it, the technical definition of a loop in the space is it is the image of a continuous map from the circle. And topologists make a distinction. So here I've drawn a picture of my torus, and I've drawn a blue loop, and I've drawn a red loop in the torus. And a topologist would call this red loop a trivial loop in the torus, because it is the boundary of a disk in the torus. Okay, so right, it's the boundary here. I can fill in this little disk here inside my loop. And so, right, somehow that makes this loop degenerate from the point of view of this sort of topology. And so these are called trivial loops. In contrast, this blue loop here, this loop is not trivial, which is something that may be hard to, it's not, I think, totally obvious how to prove that at this point, but I can tell you it's a fact. There is no way to, there exists no disk in my torus that has this loop as its boundary. And so a big objective study in topology, a big goal, topologist goal, is to understand the non-trivial loops in a topological space. And so, there's a question. Are loops considered trivial if they're homeomorphic to each other? If so, how do you determine which loop is the representative non-trivial loop? I'm not entirely sure I understand the question. In a sense, all loops are homeomorphic, or at least all embedded loops are homeomorphic to each other. I'm not sure I understand the question.
Like if you could draw 2 loops on the like on the torus, for example, that has genus 1 on the side, say one of them is just like the same loop but just bigger, would that make one of them trivial while the other one is not?
Oh, I see. So you're saying what would happen like if I also considered this green loop as is that what you mean by making the blue loop bigger?
Yeah.
Yeah, awesome. Oh yeah, so so that's a great comment. So there is this is way beyond the scope of today's talk, but there is a formal way that topologists have to capture the idea that somehow the blue loop and the green loop are the same. There's a notion of what's called homotopy, and somehow the idea is that we can like continuously drag the blue loop through the space to make it, to like push it on top of the green loop. So the key word there is homotopy. These 2 loops are homotopic to each other, even though they're different loops. So that's right. So a topologist would say both the blue loop and the green loop are examples of non-trivial loops. But when we study our loops up to homotopy, we would say that the blue loop and the green loop are somehow the same loop in the space. That's absolutely true. And that was a detail I was planning to brush under the rug today, but I'm glad you brought it up. And to drive that home, let me emphasize. So the blue loop, I can say, right, the green and blue loops are in some sense the same. Your instinct is absolutely right. They're the same in that they're homotopic to each other. And they're distinct. It turns out this is also not obvious, but they're not homotopic. This is not the same as those 2 other loops, this white loop that I've just drawn around the handle. And so, right, absolutely. So somehow a topologist would further want to distinguish not only which loops are trivial and which ones are non-trivial, but they would want to study these homotopy classes of loops. And so the green loop and the blue loop somehow represent the same homotopy class. And this white loop, it turns out, is a different homotopy class. And we get this more refined question of what are the homotopy classes of non-trivial loops in our space. Yeah, so that's a great observation. And that yes, studying these homotopy classes of loops really gets to the heart of a lot of topological features of a space.
Thank you.
Yeah, thanks for the question. And I wanted to, let me see, go back to slide number 3. Now that we know about this concept of loops, we can answer this question of how do we know a disk and the circle are not the same topological space. And one way that a topologist can prove that, if they're so inclined, is that it's a fact. I think this is not totally obvious, but it's a fact that every single loop in the disk is trivial. So any loop in the disk bounds a disk, or sorry, any loop in the disk bounds a disk. That's right, is the boundary of a disk. In contrast, the circle has a non-trivial loop. In the circle, the loop that just loops once around the circle is a non-trivial loop. And in fact, it has infinitely many non-trivial loops because there's also a loop. The loops don't need to be injective, it turns out. So there's also a non-trivial loop that like loops twice around the circle, or loops 3 times around the circle, or loops backwards around the circle. Turns out those are all different loops from the point of view of this study of loops in topology. I guess depending on, maybe I should be careful. If I view loops as maps from a circle and not just the image of a map from a circle, I have to be careful about that distinction. But right, the upshot is that to a topologist, all the loops in the disk are trivial, and all the loops, this circle has tons of non-trivial loops. And there's a great question. Are there any trivial loops in a circle? Yes, absolutely. So I could define a kind of dumb map from a circle to my circle. I could just like, wrap my circle to here, but then like wrap it around backwards again. And right, I guess it turns out that if I map my circle, instead of looping it all the way around, if I just map it onto a little line segment and then let it double back on itself, it turns out that that's an example of a trivial loop. And we'd have to get technical in that case about what I mean by the phrase, it's the boundary of a disk. But it is in fact possible to then map a disk into the circle in such a way that my original loop, that map from a disk, restricts on its boundary to the original loop we started with. And in that sense, this little circle, this loop here that doubles back on itself, is the trivial loop. So yeah, so absolutely, all topological spaces are full of trivial examples of trivial loops. And not all of them have non-trivial loops, but the circle does and the disk doesn't. So this is a way a topologist can tell that those two spaces are not homeomorphic to each other. Yeah, these are great questions. Keep up the questions. Cool. So where were we? Oh yes, we were talking about loops. Oh, and then we were going to talk about moduli spaces. So I'm back, I think, on page 4 of the Jamboard. And right, this is specializing a little bit more towards my own area of research. I'm going to talk, hopefully eventually I will actually have time to talk about configuration spaces a little bit. But in that direction, they are examples of moduli spaces. So let me say something about what a moduli space is. A moduli space, the term moduli space basically means parameter space. So this is an example of a topological space, and that parameterizes some collection of mathematical objects. So every point in my moduli space corresponds to some mathematical object. And something amazing is that somehow naturally, in many instances, collections of mathematical objects come with a topology in a natural way. So some examples of moduli spaces that are studied in mathematics. One example is the set of possible metric structures on the torus. Or really what's more interesting is what we'd call flat metric structures. This is something extensively studied. Okay, whatever that means. Another example, if you've seen some linear algebra, then, for example, the set of 10-dimensional subspaces in Euclidean space of dimension 2022, that is an example of a moduli space. And there's nothing special about the numbers 10 and 2022. You could take your favorite vector space and look at all k-dimensional subspaces, and it turns out that set of subspaces naturally has a topology, and it's a moduli space. It's called the Grassmannian. And well, I will hopefully actually have time to at least define in the talk are configuration spaces. Okay. So again, to bring home what I'm trying to say with these examples, in this example of the set of 10-dimensional subspaces in this massive dimensional Euclidean space, what I mean by that moduli space is, I mean, there's some topological space. I have a set with a topology, and somehow, it's often denoted like this, I have a set with a topology, this GR set, and in this topological space, every point corresponds to a particular 10-dimensional subspace of R to the 2022. So this is just the set of subspaces in this vector space, and somehow this set comes with its own topology. It's called a moduli space, and often studying the topology of these moduli spaces can tell us something about the objects. In this case, they can tell us something about the nature of 10-dimensional subspaces of this vector space. Something about that is captured by the topology of this space. So I propose we're going to construct a toy example of a moduli space, just to give us a sense of what these things look like. And this is something, this is not an extensively studied moduli space. I just made this up for the purpose of this talk. But I propose that we construct a space that parameterizes triangles in the plane with perimeter 1. And really concretely, I want to pin down what I mean by these objects. So first of all, I'm going to label the edges of the triangle. So whenever I draw a triangle, it has edges L1, L2, and L3. And this would not be considered the same as a similar triangle, but with different labels on the 3 edges. So I'm actually going to keep track. I'm going to talk about the first edge, the second edge, and the third edge. And I'm going to keep track of which are which. But if I have 2 similar triangles with the same 3 edges labeled, I'm going to consider them the same triangle. And this assumption about labeling edges is just going to make our construction a little bit easier on ourselves. I'm happy to talk about what we could do differently if we wanted to drop that assumption. Okay, so our goal is to construct a topological space where each point in the space corresponds to a triangle that has perimeter 1 and has edges L1, L2, and L3. Okay, so let's move on to slide number 5. All right, so I think a fact that you maybe believe already is that a triangle in the plane is determined by its edge lengths. So in order to specify a triangle, we really just need these 3 numbers, the lengths L1, L2, and L3. And additionally, we've imposed this condition that the sum of the 3 edges is 1, the perimeter is 1. And so that means if I know what L1 and L2, if I know 2 of my edges, then I know what the third one is by this condition. So it's determined by the 2 real numbers, L1 and L2. And something that I encourage you to think about if you haven't already, but you could ask this question: if we're given 3 real numbers, L1, L2, and L3, under what extra conditions will those 3 real numbers be the edge length of a triangle? And I claim that the conditions are exactly the following. I just need to make sure that any pair of these 3 numbers, that their sum is greater than the third edge length. And that's the one condition I need to guarantee that these 3 edges form a triangle. So specifically, we have the 3 conditions. L1 plus L2 has to be greater than L3. L1 plus L3 has to be greater than L2. L2 plus L3 has to be greater than L1. Oh, and I guess they all need to be, oh, in fact, strictly positive numbers. Okay, so in order to specify the set of triangles in the plane with labeled edges up to similarity, what we need are 3 real numbers subject to this list of conditions. And this data exactly determines the set of triangles in the plane perimeter 1 up to similarity. Okay, I'm going to leave it as an exercise that you can actually simplify this list of conditions. So if you just do some algebra, this is just an algebra exercise. This reduces to the following rule. We need L1 and L2 with the following list of conditions. So first of all, L1 needs to be positive and it needs to be less than 1/2. L2 needs to be positive and it needs to be less than 1/2. And the sum of L1 plus L2 has to be greater than 1/2. I claim that if you combine, just do some algebra to combine this list of conditions, you will come up with this list of conditions. And implicitly, the third length L3 is 1 minus L2 minus L1. Okay. And so, great. So now we have this correspondence. We have a bijection between triangles of perimeter 1 up to similarity with labeled edges. That set of triangles is in bijection with pairs of real numbers, ordered pairs of real numbers, L1, L2, subject to those 3 conditions we just wrote down. And so if I view this pair of real numbers as a point in the plane, it's an ordered pair of real numbers, then we can in fact interpret this moduli space as a subset of the real number line. Let me draw that subset. Okay, so here's the boundary x equals 1/2. Here's y equals 1/2. And then here's x plus y equals 1/2. So I need pairs. The conditions tell me that my pairs need to be above this diagonal. Oops. The 3 conditions exactly tell me that my ordered pairs need to be in this region here. So this triangular region of the plane, of the Cartesian plane, is our moduli space of triangles. And as promised, every point in this moduli space corresponds to a triangle. So here, this is the point. I don't know what point this is. Let's say this is the point, I don't know, 1/4, 1/3. Then this is going to correspond, this point corresponds to a triangle. Let's see here, it's got an edge of length 1/4, an edge of length 1/3. In fact, the edges are labeled. So this is edge number 1 has length 1/4. Edge number 2 has length 1/3. And if I've done my arithmetic correctly, the last edge has length 5/12. Okay. And so, right, again, every point in this triangular region corresponds to one of our triangles, and every triangle corresponds to some point in this region. And the topology, I mean, this is a topological space. We know what it means for points in the space to be close to each other. That tells us something about the nature of these triangles. It gives us a notion of when 2 triangles are close to each other, if these 2 points are close in the space. Okay. So we're trying to see in this example that this is supposed to illustrate that the topology of a moduli space tells us something about the objects that parameterizes. And here I'll make an example of an observation. This region in the plane, this is path connected. In fact, topologically, it's just a disk. The moduli space is path connected. And that already is capturing a fact about these triangles of perimeter 1. So I've tried to draw here, I've drawn here a picture of a path through my moduli space and a sampling of points along the path. So each of these points corresponds to a triangle. Here's a triangle here, and this one, the x coordinate's kind of small. So here's the first side of the triangle is kind of small, and like the y coordinate's kind of big. So the second edge is kind of large. And then as I move along this path, the x coordinate gets bigger and bigger. So the first side length gets bigger and bigger, and the y side length gets smaller and smaller. So I'm moving from a triangle that looks kind of like this to a triangle that looks kind of like that. But anyways, what I want to take away is that the existence of this path between these two triangles is telling me how I can continually deform this triangle into this triangle through a family of triangles of perimeter 1. And the statement that it's path connected says that you can always continuously deform any perimeter 1 triangle to any other through a family of perimeter 1 triangles, in the sense that's sort of sketched here. As you move along this path, this edge is continuously getting bigger, this edge is continuously getting smaller, and at every stage I have a perimeter 1 triangle. So this is sort of a toy example, but I think this illustrates this sort of connection between the topology on the moduli space and the nature of these triangles that we're studying. And this is the idea behind looking at moduli spaces. So I think I only have about 8 minutes left in the talk. So let me, in the last 8 minutes, I will define what a configuration space is. And I will leave you, I think in the last slides, there are some exercises. Okay, so let's move on to page 6. All right, configuration spaces are examples of moduli spaces. They're the spaces that I sometimes study in my research. I'm really interested in what the topology of these spaces are, which is a big open question. There's tons of mathematicians that are doing work on this, and it's something that connects to a lot of different fields of mathematics. So that this has connections to algebraic topology, to geometric group theory, to algebraic geometry, to combinatorics, to many others. Even PDE and robotics have connections to configuration spaces. So they're objects that are really interesting, but there's tons we don't understand about their topology. We don't even understand the topology in the case of the configuration space of a torus. So I think this is a very interesting class of objects. And with that said, let me actually define it for us. Okay. So here's the setup. I start with a topological space X, which you can think it might be a line or the plane or a torus, or choose your favorite topological space. And by definition, the ordered configuration space of n points in X, which I'm denoting Fnx, is the space built as follows. So an element in the space is an n-tuple x1 up to xn of distinct points in X. So an ordered list of distinct points in X. And here's an example. If X here is my topological space, this like squishy red thing, then I've chosen 3 points in my space, which I've labeled X1, X2, and X3. So this choice of 3 points, this corresponds to 1 point in my configuration space. And so as a set, the configuration space is the set of ordered lists of n distinct points in X. And again, these configuration spaces come with a topology. So the way to view them as a topological space formally is first we take the Cartesian product of X with itself n times. Okay, we take the product. So this product naturally has a topology on it. And the product is the space just of all ordered n tuples without this distinctness assumption added on. Okay, so to get from the Cartesian product to the configuration space, we need to pass to a subspace. We need to delete all tuples where any of the pairs of points coincide. So I delete from my Cartesian product all of the points where 2 or more of the coordinates are equal to each other. Those would be the points where, like, if X1 and X2 were kind of both this point right here, that's not in my configuration space. It's in the Cartesian product, but not in the configuration space. So I delete those. And let us, hopefully we have time, let's take 3 minutes to work through this example of the configuration space of the closed interval on 2 points. So our construction says I start by taking the product of the interval with itself, which is a square, and then I delete the set of points where the 2 components are equal to each other. So that is exactly, I'm going to delete this line defined by the equation x equals y. That's the line of all the tuples where both points are the same. And so what I get is this is my configuration space on 2 points. It is these 2 disjoint triangles. And I can view in this space, I can view every single one of these points in my space corresponds to a configuration, which I can draw a picture of like this. Here's one. So maybe this point here, say this point right here might be this configuration, for example, drawn from this other perspective. And again, I can view paths. I can interpret a path in my configuration space as a family of configurations. So in this path, see what's happened in this path, the x coordinate is fixed. The x coordinate is not changing as I move along this path from here to here. And so that means throughout this family, the point x1 is standing still. But as I move down here, the y coordinate is getting bigger. And, oh, I'm sorry, it's getting smaller. And so I should view this as a path of configurations where I am taking my point x2 and I'm sliding it to the left along the number line. Okay, so again, I can view paths in this configuration space as these families of configurations where I'm sliding my 2 points around continuously. And again, it is topologically meaningful. It is telling me something about the nature of these collections of points in the line, that this configuration space is not path connected. So it fails to be path connected because I have this one configuration. This configuration up here consists of all of the points where x1 is bigger than x2. And this second component down here consists of all the points where x2 is bigger than x1. And the reason the space is disconnected is because we cannot slide the point x1 past x2 without having a collision of particles, which is not allowed in configuration space. So there's no way that I can slide these 2 points past each other without the 2 points overlapping at some point. But the point where they overlap, that's on this diagonal. That's not a point in my configuration space. And so there's no way I can move continuously through configuration space to get from a configuration where x1 is on the left to a configuration where x1 is on the right. Okay. And I've left for you as an exercise, this is a little bit tricky, that in general, the configuration space of the interval has n factorial components. And an even trickier exercise is to check that topologically each of those components is a disk. Okay. And oh shoot, I'm over time. I'm gonna cheat and take one more minute. I'm gonna go one more slide ahead. And just as a teaser, so this I will leave for everyone to consider on your own time if you're interested. Oh, first of all, is this blurb saying that I study the topology of configuration spaces. It's relevant to a lot of areas of math, and yet there's a lot we don't understand. So I think that's interesting. But what I wanted to point out is there's another worked example here of an example of the configuration space of the circle. And it turns out so I challenge you to work through this exercise to check that the configuration space of the circle on 2 points is topologically the same as a cylinder. And the key to doing that is to make friends with these gluing constructions so that you can draw the pictures in this way. And then there's a list of additional exercises that are there for your enjoyment. So let me stop here. Thank you for your attention.
Yeah, thanks for a great talk. So are there any more questions? Oh, I have one question for the Jamboard link. Yes, let me resend the link where you can find all of these questions. Yeah, any more questions? Okay, here's a question. Oh, here's a question. In a 3-manifold, are all loops homotopic to a loop on its boundary? I think for a general 3-manifold, the answer to that question is no. Although that's a little bit harder to visualize. It's also, I mean, not all 3-manifolds have boundary, which also makes the question a little more subtle.
Oh, the question, how difficult was it to come up with the example of the moduli space of perimeter 1 triangles? I would say not difficult, or how, maybe I don't understand the question. The goal was to come up with an example of a moduli space that we could sort of naturally draw as a subspace of the Euclidean plane, because that's a situation where I think folks understand that the topology, even if they haven't, acclimated to the definition of topology, we understand subsets of the plane. So, right. So it was just a matter of thinking up, what are mathematical objects that are parameterized by a list of numbers, ideally a list of 2 real numbers. And so that lent itself to working with triangles. But there are, there are tons of warm-up examples you could think about of moduli spaces. I think another popular one is, I claim that if you look at, take the Cartesian plane and think of the space of rays that start at the origin and emanate outwards. So there's a set of such rays, and I claim that the moduli space of those rays has a topology, and it's naturally the circle. It's naturally the unit circle, in fact. So that's another very popular example, warm-up example of a moduli space. Awesome. Oh, I'm so glad to hear that. Thank you. I'm glad it was pedagogically effective. Question. When is there a way to add a point to the configuration space of n-ordered points so that all the points are distinct? Oh, brilliant question. So there are 2 different, let me give 2 answers to this question. Let me scroll back to our picture. In fact, we can just scroll back to our picture of these examples of points in the moduli space of the interval. So I think I went through everything on configuration spaces quite quickly. So I hope, if you're interested, you can think about this in a little more depth, and how kind of this weird back and forth between this topological space and each point in the space as a picture that we can draw like this. And in fact, sorry, I'm sidetracked, but let me finish this thought. Being able to think about the topology of this space in terms of continuously manipulating pictures like this is really important for what I do, because once n gets larger, every time I increase n, the dimension of the space goes up. And so even if I want to think about n equals 4, for example, I just can't plot, I can't think in 4 dimensions very effectively. I can't draw a picture of the space anymore. So it's much harder to be able to understand the topology by drawing a picture like this. And instead, I need to understand the topology by thinking about how I can manipulate points. How can I continuously manipulate points in the interval, or in whatever my space is? So it's a good challenge to kind of think about this back and forth, and this kind of dictionary between points in my topological space and pictures like this one. Anyway, sorry. So to go back to this question, when is there a way to add a point to the configuration space so that they're all still distinct? And one answer is, if I fix a particular configuration, so if I take this picture here, then this is a naive answer to the question, I can always add another point, because the interval, unless my space X has only finitely many points, which is not a very interesting case of when you're studying configuration spaces, or at least not for the sort of math I do with configuration spaces. If X only had finitely many points, then eventually I'd run out. I would, if X was a space with 10 points total, with a topological space with only the underlying set and only 10 points, then it would make sense to talk about the configuration space of 1 or 2 or 3 or up to 10 points, but there'd be no configuration space on 11 points. I just ran out of points. The real line has an uncountably infinite number of points, whatever that means. It has a ton of points, so many points. So if I fix a point in my configuration space, and that takes up 2 of my infinitely many points, I can always add another point. I could always, like, I still have an infinite number of options to choose from for a 3rd point and a 4th point and a 5th point, and I'll always be able to add another point if I start with a specific configuration and I keep adding points. In contrast, a different question, which is actually like a question that's being actively studied by mathematicians, and there's some recent research papers on this from the last few years. So one way to interpret this question, I'll write in the chat. This question is, when is there a map from the configuration space of X on n points to the configuration space of X on n+1 points? So when can I take any configuration in X and introduce another point, right, that takes x1, x2 up to xn to I start with my first, this map has to operate in the way that my first endpoints stay the same, and then I add an n plus first point. Okay, so again, if X has an infinite number of points, there always exists functions to do this. I can always just like take my n points and just like, choose some point in X that's not already in the list. But a much more subtle question is, when can I do this continuously? Like when does there exist a map of this form that is continuous with respect to the topologies on F and X and F n+1 X? And the answer is sometimes this is a subtle question that is the subject of a lot of research. Okay, and this might not be obvious, but it's possible to do this. It's always possible to do this. Oh yeah, what do I mean by an object having a topology? That's right. So, right, the technical thing that I mean is that we have defined what's called a topology on the, so an object with a topology, it's a set with a topological structure. The formal definition is that means I've like formally declared what it means for subsets of my objects to be open subsets. That's the formal technical definition of a topology on a space. And I think that that definition is definitely too hard to get to wrap our heads around if you haven't seen it before. So let me say that there's some formal definition that exists, but informally, I would say that I have defined extra structure on my set that lets me make sense of operations like continuous maps or like continuous manipulation of my space. And that's not very precise, but to make yourself happy with that, I strongly encourage you to just think of this list of examples of subsets of Euclidean space that we've talked about. Subsets like lines and planes and circles and tori and genus 5 surfaces and, disjoint collections of points and all of these examples. And when we're working with those objects, you really can kind of intuitively grasp what it means to like imagine that this object is made out of putty, so you can continuously manipulate it, or you can draw a continuous path in it and you sort of instinctively know what that means, even without worrying about the formal definition. Oh, and the question is, why is it significant that we study an object's configuration space? Do you have a concrete example of why this is helpful? Yeah, that's a great question. And there are, I guess there are many answers to that question. So it comes up in a lot of different ways. A sort of vague but like fairly universal answer is that it often comes up in, I mean, it often comes up that different people are studying in whatever area of math, they kind of naturally study families of objects that somehow involve the data of a finite set. And then somehow to study their family of objects, it becomes relevant to study this family of all finite sets, in this case, finite ordered sets in the space, and like the topology of the configuration space becomes relevant to their family. So let's like specialize to a particular example. If we are studying, let's say I'm interested in polynomials, the study of algebraic geometry is all about polynomials. And so polynomials, big deal in mathematics. Let's say polynomials, let's just say polynomials with real coefficients. Although this gets even more interesting if you've taken some complex, if you've studied the complex numbers, the story gets way more interesting if you're willing to work with polynomials with complex coefficients. But if I'm studying polynomials with real coefficients, then at least in some cases, if I have a polynomial that I can factor, then that polynomial is determined by its set of roots. That's not true for all real polynomials. It is true for all complex polynomials. If I'm only looking at real roots. And so if let's say I'm studying the class of polynomials, let's say degree n polynomials that factor completely into n distinct roots, then that collection of polynomials is something that I can relate. In fact, that collection of polynomials is exactly the degree n configuration space of the real line. And the topology of that degree n configuration space of the real line tells me something about polynomials. And in fact, again, for this next comment, I think you would have to work with complex polynomials. But it turns out that there are some really deep questions. I mean, there are some very classical, like hundreds and hundreds year old mathematics questions about like, when is it possible to solve a polynomial by radicals? Like how, there we have the quadratic formula that lets us solve degree 2 polynomials. Does it have an analog for higher degree polynomials? And it turns out that you can reframe these questions about the existence of solubility by radicals of polynomials. You can reframe that in terms of topological questions about configuration spaces. So that's an example of the sort of place where configuration spaces come up. That was a lot of words, but I hope polynomials is one example. Turns out homotopy groups of spheres is another example. And that phrase shouldn't mean anything necessarily to folks here, but let's just say it's a massive area of algebraic topology, and somehow it's deeply related to configuration spaces in the plane in some mysterious way. I'll just keep talking about this. Another cute example that is currently being studied in robotics. I know less about this. This is an application I don't have a lot of background in, but a model for if you are interested in modeling how to get robots to, for example, move along a factory floor in an efficient way, for example, then you can model your factory as a graph, as like a collection of line segments kind of glued together at points. You can model your factory floor as a graph, and each of your robots is a point in that graph. And then distribution of where in your factory the robots are, that is precisely a point in the configuration space of this graph. And so there's some work being done studying what's called robotic motion planning, where they model ways to understand the movements of robots around your factory as in terms of the topology of configuration space. And in this case, like, you're very interested, I want my robots to be able to move around efficiently, and I definitely don't want them to collide with each other. That's bad if I have robots. And so somehow the topology and invariants like loops in my configuration space are related to this question of how I can instruct my robots to move around my factory. So that's another applied application of configuration spaces. Oh, the next question is, how do you find a good approximation of like putting X into the ordered configuration space? I'm not totally sure so the word approximation could mean different things in this context, but in general so this is closely related. I mean, X is the same as the configuration space on one point in X. And so this question of finding maps, continuous maps from the configuration space of just one point on X into the configuration space of n points on X, this comes back to the other question about, do we have continuous maps between configuration spaces? Like, can I continuously add new points in a way that is globally across all configurations, a continuous operation? And the short answer is the maps, those continuous maps of that form just don't exist in general. So in general, for a general space X, there is no good way to embed X into its configuration space in a kind of subject to these conditions that, like, I want X to be the first component of the configuration. And there are exceptions. There are spaces where you can do this. I claim, and this shouldn't at all be obvious, but I claim that with the line segment, let's say the open line segment, not the closed line segment, but if you take an open line segment, you can embed X into its configuration space. But if you are working instead with the circle, in contrast, you can't. There's no, at least for my notion of natural, there's no natural way to embed a circle into its configuration space. Like, there's no natural way that you can keep adding points in a way that's continuous over any starting choice of configuration. So despite the fact that I can't necessarily embed X into its configuration space, I would still say that the configuration space is a good kind of invariant of a topological space X, in the sense that it's a way that I can distinguish between different topological spaces. So for example, if you look at the exercises at the end of the Jamboard, if I take the configuration space of an interval on 2 points, it's disconnected. If I take the configuration space of a plane on 2 points, that is connected. And this is, I think, conceptually tricky to unpack, but roughly that comes down to the fact that if I have a whole plane and I have a configuration of 2 points in the plane, I have a different configuration of 2 points in the plane, it will always be possible for me to continuously nudge one of those configurations to the other. I can always slide my points through the plane. There's enough space that they can do that without colliding with each other. So it turns out that the configuration space of the plane on 2 points is path connected. And so that distinction between the topologies of the configuration space of the interval and the plane, that tells me that the interval and the plane are not homeomorphic to each other. So even though I don't have good maps of this form, I would say that configuration spaces are still a useful invariant because their topologies still let me distinguish between non-homeomorphic topological spaces.
Are there any final questions? Oh, okay, there's another one.
Oh, what would the configuration of a graph look like? Oh, that's a great question. So let me move forward to just to the on slide 9. I tried to draw some pictures. These are actually the unordered configuration space. These slides just keep going and going and going. There was a lot of content. So here's an example of a graph. And right, some bad news about studying configuration spaces of graphs is that, like in the example in this graph here, this little pinwheel guy, I can't draw this graph kind of in one dimension, even though it's somehow a one-dimensional object. To actually draw it for myself, I need to draw it in the plane. And that's bad news, because it means that somehow, even to draw the configuration space on 2 points in this graph, I would need to start by taking the product of the graph with itself. And like already I don't know how to visualize that. Already that is too high dimensional an object for me to like look at and study. This is something that lives in 4-dimensional space. And who knows how to think about that. And so in order to study the topology on the configuration spaces of a graph, it's of a general graph, I'm kind of out of luck in terms of actually just drawing and looking at the configuration space in the way we did with the interval. What I have to do is actually think about collection, like I have to think in terms of these pictures of collections of red points in my graph and how they can continuously move around. And what this picture, this is actually the unordered configuration space. So if you're really keen, you can read ahead in the notes and see the definition of the unordered configuration space, where I'm just looking at subsets instead of ordered lists of points in my space. So in this universe, all the points are indistinguishable from each other. I don't know what point 1 is and what point 2 is. Okay, and here is a picture. A picture in a series of snapshots of a loop in the configuration space, a non-trivial loop in the configuration space of the graph, where I start, I guess you can't, I'm not sure if you can see my mouse, but I draw this loop. I'm talking really quickly. I hope this is actually useful for everyone. But this is right. So this is a picture of a loop in a series of snapshots, the unordered configuration space. I start here. This is just one point in my configuration space. This is the starting point in my loop. First, I take this particle and I slide it down here. Now I have this point in the configuration space. Now I take this particle and I slide it down here. Now I have this point in the configuration space. Now I take this particle and I slide it back up here. Now I have this point in the configuration space. And now I take this particle and I slide it up here. And I'm back to my starting point in the configuration space. So that's a loop. And something that is by no means obvious, but it turns out this loop is non-trivial. It doesn't bound a disk, whatever that means. And so in answer to the question, what does the configuration space of a graph look like? I mean, I don't know, that's too high dimensional for me to think about directly, but we can study it by drawing pictures like these. So I just drew you a loop, a non-trivial loop in that configuration space. I think it's really cool too. I think this stuff is so cool. Yeah. Thank you.
Well, if there are no more questions, so thanks again for a fantastic talk. And now I guess we'll move on to my part of the class. So let me end the recording and get set up.